Thank you very much. Can you hear me and can you see my slides
Yes, you're
before we get
all ready to
started?
go. Thank you, Gemma.
Fabulous. Thank you very much. Yeah, thank you very much everyone for coming. So yeah, my name is Gemma. I'm a lecturer at the University of Bristol. I'm also the program director from Mechanical Engineering program and the hydrogen storage theme lead for GW Shift. I've got a research interest in hydrogen storage. I've also got a research interest in life cycle assessment, particularly the uptake and implementation of renewable technologies like hydrogen, but also things like batteries and heat pumps. So a little bit about my background. I am a former chemist. My undergraduate was actually in chemistry, and then I turned to the dark side. I turned to engineering during my PhD, where I was researching hydrogen storage in particular. So thank you very much for joining us. If you have any interest in hydrogen storage or even more broadly in like life cycle thinking, engagement and renewables, then please feel free to get in touch. You can obviously, our details are all on the GW Shift website and my email is here on the slide as well. And let's get started. So just to give you a summary of what I'm going to cover. We're going to go through first a whistle-stop tour of hydrogen, just in case you missed any of our previous seminars, just kind of like highlight the key points about hydrogen. I'm then going to talk a bit more broadly about energy storage considerations before I go through our kind of main and upcoming hydrogen storage technologies, and I'll finish with a little bit of a future outlook. So without further ado, whistle-stop tour of hydrogen. So hydrogen, it is the smallest, lightest, and the most abundant element in the entire universe. And there's some really key advantages into using hydrogen as a fuel. The first is that we can effectively have a limitless supply. You can make hydrogen from water by splitting it with electricity into hydrogen and oxygen. You can then use that hydrogen either by combusting it in an engine or reacting it in a fuel cell, and the only byproduct is water. So it could be this completely green, completely clean cycle. And this is why people get very, very excited about hydrogen, because it could be this potential solution to a lot of our energy problems. Another key advantage of hydrogen is that by weight, it has a very high energy density. And this is why rockets use liquid hydrogen as a fuel. That big kind of orange tank in the background there, half of that is filled with liquid hydrogen. And if we can effectively meet our energy needs with rocket fuel and produce only water, part of the big question is why aren't we using hydrogen everywhere already? And I personally like to split this into there's three main areas of research for hydrogen, which is making it, storing it, and using it. And I'm going to seamlessly signpost you to our previous seminars at this point. Tim gave a really nice overview of hydrogen in general, and James Courtney in our last seminar looked a lot more at that hydrogen production side of green hydrogen. And today I'm going to be talking to you about the storage part of hydrogen. So fab. So the problem with hydrogen is really all about energy density. And I'm going to illustrate this problem using the example of a car. So by weight, hydrogen has the highest energy density of any fuel known to mankind, which is actually pretty awesome. To give you an example, if you were to drive a car from London to Birmingham and back again, that's a journey of approximately 250 miles, about 400 kilometers. You would need 24 kilograms of petrol to make that journey. But if you were to use hydrogen, you'd actually only need 8 kilograms of hydrogen if you reacted it, if you used it in a combustion engine, or even less, 4 kilograms of hydrogen if you reacted it in a fuel cell. The problem comes with hydrogen is that it's a gas, so it has a very low volumetric energy density, which means it just takes up a lot of space. So that 4 kilograms of hydrogen, even though we don't actually need that much by weight, it takes up a volume equivalent to about 45 meters cubed, which is the same as a gigantic sphere of about 5 meters in diameter. Or looking at it a different scale, my favorite scale, the party balloon scale, that's equivalent to about 600 party balloons. And you can count them, I promise you there are 600 there. So there's not really a feasible storage solution for storing hydrogen. And so this is kind of where the energy density comes in. So hydrogen has a very high gravimetric energy density. This is the amount of energy that we store per kilogram, per mass. It kind of tells us how heavy our fuel is. But it unfortunately has a very low volumetric energy density. This is the amount of energy per liter, sort of how much space our fuel takes up. So if we kind of compare hydrogen to some common fuels, you can start to see where the challenge lies. Now, our usual fuels, our fossil fuels, petrol, diesel, kerosene, they're actually a pretty perfect balance of this kind of gravimetric and volumetric energy density. And this is partly why they're so difficult to replace, because they have enough power for us to, enough energy, for us to power our cars, generators, planes, but without taking up too much space. If you look at natural gas, now the gas itself has a very low volumetric energy density, but we can compress it, we can liquefy it, we can increase that volumetric energy density, and liquid natural gas is used frequently as a fuel, and it's used quite frequently to transport natural gas as well. Looking at the other side, looking at batteries, compared to fossil fuels, batteries don't have quite the same energy density, but their small size makes them really perfect for our portable devices. But for larger applications, things like electric cars, grid storage, you need a battery stack. You need lots of batteries in order to get that energy density. Now, if we look at hydrogen, you're kind of going straight to the far right here. So by weight, again, is the fuel that contains the most energy, and that's why we use it as a rocket fuel. But by volume, it is objectively terrible. Like natural gas, hydrogen needs a lot of space, and with hydrogen storage solutions, what we're really doing is looking at improving that volumetric energy density without trying to compromise too much on the gravimetric energy density. So let's talk briefly about some general storage considerations. So as with any storage method, it really depends on your application. And this image on this slide here shows you some sort of discharge versus capacity times for some grid scale energy storage technologies, but the same principles apply with any storage solution. You've always got to ask yourself 3 questions, which is how much energy do you need? How long do you need to store it for? And how quickly do you need to get that energy back out again? Now, looking at hydrogen, we've got a variety of hydrogen storage technologies available to us, illustrated by the example on this slide. And they vary in terms of the cost, the capacity, the scale, and the technological maturity. But again, we're still asking ourselves the same question. The choice depends on how much energy you need, how long you need to store it for, and how quickly you need to get that energy, that hydrogen, back out again. To give you an example of what this looks like in practice, so the US Department of Energy have a famous in hydrogen, a famous set of targets for onboard storage of hydrogen. This is the storage of hydrogen in light vehicles like cars. This table is just a little excerpt of those targets, and you can see you've got the gravimetric energy density, you've got the volumetric energy density, and the system cost. If you have a look at the website, which I've linked, I've linked it on this slide, then you'll kind of see a whole list of targets, including things like refill time. Now, these targets have been set using real driving data with the market in mind. Those ultimate targets on the right-hand side, where they want to get to, is what is considered to be a commercially viable and competitive storage system for a hydrogen car. The system is important to, I think, recognize is the system does not need to be perfect, but it does need to be good enough for your application, whatever that application may be. And researchers and manufacturers, when we're looking at our hydrogen storage systems for, in this case, for vehicles, this is the kind of thing that we have in mind when we design those storage systems. Something that's really worth noting at this point is that these targets on this slide, these are for the entire storage system. So that includes your stored hydrogen, whatever medium you're storing your hydrogen in, as well as the components and everything else that makes up the full storage system. And that's important for any storage system, but particularly for hydrogen, because we'll see some examples later where we might see some really decent, really good looking storage capacities, but it's about the medium and the material that they're in, and they've not really considered the full storage system. So that's just something to be aware of there. It's not just about the storage medium that you're using, it's about everything you need to support that storage as well to give you your capacity. So let's talk a bit more about how hydrogen is actually stored. Now, you can kind of split hydrogen storage methods broadly according to physical and material-based methods. By physical, we are in some way altering the state of hydrogen to increase its energy density, its volumetric energy density. You could be compressing it to a gas, or you could be cooling it to a liquid, for example. With materials-based, you are storing hydrogen on the surface of a solid, or in a process known as adsorption, or within a solid, a process known as absorption, and then you extract it back out again. And it's that process of pulling the hydrogen into the material that increases the energy density. Now, this is a very valid way of talking about hydrogen storage options, and you will frequently see hydrogen storage talked about in terms of these different methods. But the way that I'm going to talk about them in kind of our discussion here is I'm going to talk about them in terms of the technological maturity. So I'm going to start with the methods that are currently used in commercial, and then I'm going to go to the methods that are maybe promising, but maybe a bit lower in sort of their technology readiness. I'm also going to say I'm not going to give you an exhaustive overview of every single hydrogen storage technology known to mankind, because we would be here forever and you have better things to do on your Friday afternoon. My goal is to give you an idea of the technologies that we have in use, those that are in development, and sort of a bit of a cost-benefit analysis, kind of what to look out for with these different types of technology. So with that, we're going to start with what I would call our primary hydrogen storage technologies. So these are, I would say we have two that I would consider mature and widespread. And these are liquid hydrogen and compressed hydrogen. So for liquid hydrogen, we are storing hydrogen as a cryogenic liquid. This is where you cool hydrogen down to minus 253 degrees Celsius, which is 20 Kelvin, very cold, to liquefy it. Can be pressurized, but the pressure is not typically very high in these systems, sort of maximum about 10 bar. And the alternative is compressed hydrogen. This is where you're storing hydrogen as a compressed gas. Depends on the system, but usually somewhere between 150 and 300 bar. So we'll start with liquid hydrogen. So you need to cool it down to minus 253 degrees, and you store it in these cryogenic, well-insulated storage vessels. You've got this example here at Kennedy Space Center of a liquid hydrogen storage vessel. And this is to minimize the heat transfer, so we can keep that hydrogen cold. In terms of advantages, pros, it does have a high volumetric energy density for a hydrogen storage solution, about 8 megajoules per liter, compared to diesel and petrol. They're about 32, so it's not as high as there, but you know, this is reasonable, this is decent. We can do something with liquid hydrogen. It has faster refueling compared to something like compressed gas, and it is a mature technology. This is being used right now. It's used in several industries, particularly for stationary storage. In terms of disadvantages, liquid hydrogen is very energy intensive. If you take your hydrogen and you liquefy it, about a third of that energy, you need about a third of that energy just to turn it into a liquid, just to do that process. So it is very energy intensive. It is, of course, cryogenic, so we keep it in these well-insulated cylinders to minimize that heat transfer and keep it in a liquid state, but we still do get some heat transfer. We still do get some loss of hydrogen over time in a phenomenon which is called boil-off. What happens is that your liquid hydrogen warms up, it converts from a liquid into a gas, you get a pressure buildup in your liquid hydrogen vessel, and so you need to vent that pressure in the tank every now and then, and this is called boil-off. You, of course, have a big infrastructure requirement for your liquid hydrogen system. You need to be able to produce, transport, and then store your liquid hydrogen. And there are some safety hazards to consider, aside from the general ones for hydrogen. You've got venting needed for that pressure buildup, for that boil-off, and you're working with cryogenics, so frostbite is an issue potentially for your operators too. Example applications, heavily used in the aerospace industry. Future applications is being looked at particularly for aircraft, long haul and short haul, and also for shipping. And if you wonder how they actually fill that giant dome, this is what the filling process looks like. You can see the tanker trucks that have transported the liquid hydrogen, and they're refilling the dome here, and you can see, of course, the operators wearing their personal protective equipment. So compressed hydrogen. So at the lower end of the pressure, sort of 150, 300 bar, this is kind of where our stationary storage sits. And at the higher end, more towards 700 bar, this is where we have our mobile applications, hydrogen cars. The Toyota Mirai, for example, has two 700 bar hydrogen cylinders in its system. Now, just to illustrate, because 700 bar is a number, but I just want to illustrate how big of a number that is. So 700 bar is the equivalent of going underwater about 7,000 meters. Just for perspective, the Titanic wreck is, I think, about 3,800 meters. So this is significant pressure, and this adds some engineering considerations and storage considerations to this. In terms of pros, very suitable for stationary storage. You can use it for mobile storage. It is being used for mobile storage. It's well-established technology. It's a lower cost than liquid hydrogen, and it is mature, which is amazing. In terms of cons, it does have a more limited volumetric energy density. It ranges from about 1.5 megajoules per liter for your lower pressures for about 150 bar, up to about 5.6 at 700 bar. So it's lower than liquid hydrogen. In terms of the actual cylinders we use, you can use very cost-effective metal cylinders up to about 300 bar. but these are heavy, so they're not as efficient in terms of the gravimetric energy density, something to consider. Not necessarily an issue for your stationary storage, but for mobile applications it is. And so for mobile applications for hydrogen cars, the industry standard is using compressed hydrogen at 350 or 700 bar. And we can't use metal cylinders, so instead we use what's called a Type 4 composite tank, where you have this kind of plastic liner overwrapped with carbon fiber composite, which makes them much more lightweight than the metal cylinders, and they can withstand a much higher pressure, but they're much more expensive. You've also, for compressed hydrogen, got that additional energy cost that you need to compress your hydrogen ready for use, and you need to pre-cool it as well to prevent overheating during that filling process. In terms of applications, really widely used in industrially and commercially. In terms of future applications, hydrogen fuel cells and combustion vehicles are the two big things people are looking at. So now I'm going to go into a couple of upcoming and alternative hydrogen storage technologies. So these are technologies that have been widely used for natural gas that are being newly applied to hydrogen, as in addition to sort of newer technologies that are kind of a lower technology readiness, but kind of look promising, look exciting. In terms of technologies that are currently used with natural gas, but being applied to hydrogen, we have underground storage and pipelines. By underground storage, I mean the storage of hydrogen in geological formations, such as salt caverns, depleted gas fields, depleted aquifers. Now, underground hydrogen storage in salt caverns is the closest to commercial scale. And there's a really interesting report published by the International Energy Agency just last month, who've been looking into salt cavern storage in particular. And it's really interesting. They found that the designs and practices for the storage are very similar. Sort of the storage designs and practices that we have currently for methane are generally transferable to hydrogen, which is a massive advantage. There are some technical challenges, but they generally thought this was solvable for an additional cost. And the main barriers they highlighted are actually non-technical, which is very interesting. So underground storage, widely used for natural gas, and there are a few, but there are a small number of projects worldwide for hydrogen. In terms of pros, this is mature for natural gas. This is well-known technology. You can have a very large storage capacity. We're talking terawatt-hour scale. Volumetric energy density is lower, but when you're storing at such scale, it doesn't really matter so much. You potentially got a very low unit cost at scale, and it's a really interesting use case is using it for seasonal grid scale of renewable energy. The idea being that in your periods of high production of renewable energy, so in the summer, when it's very windy, you can take your excess renewables, use it to produce hydrogen, and then store that hydrogen underground. And then when you need it, sort of in the winter, when you have high demand, you can then remove that hydrogen and pull it back into the system and use it to grid balance there, which is interesting. In terms of cons, underground storage, very location dependent. You need to have a salt cavern or similar geological formation in order to do so. The absence of an established hydrogen economy is also a problem. You need to have the production and transport in place to support your salt cavern. This means that we need financial incentives and government buy-in to encourage and de-risk these kinds of projects. The public acceptance of hydrogen is also variable. So you need clear communication with your communities to communicate any perceived risks and the cost benefit to that local community. Also worth saying that while the underground hydrogen storage designs and practices do align with our kind of well-established natural gas ones, there are some hydrogen-specific regulations and certifications that need development, and some materials and design considerations too. And in terms of applications, we're kind of looking at larger scale storage for underground hydrogen. Wanted to highlight a really interesting project here in the Southwest. So the preliminary project design has been completed for a salt cavern project here in Dorset, I'm in Bristol, down there in Dorset, here in the Southwest. The proposal is for 24 salt caverns at about 1,300 meters of depth, and the idea is they can produce a maximum annual capacity, or they can store a maximum annual capacity of about 30 terawatt hours. Some other projects of interest that I'd recommend looking up if you're interested in this, I put below. One of them, the Lind system. They've actually been operating the world's first commercial high purity hydrogen cavern for about 15 years now at their facility in Texas. And it was designed to provide hydrogen to their customers during sort of times of peak demand, which is really interesting. So moving on to pipelines, this kind of covers the storage of gas within the pipeline network. And this is actually how a good quantity of our natural gas is stored. We do have it just inherently in the pipeline network, doing sort of the transmission and the distribution. It's known as line pack. And gas operators can vary the amount of gas stored within these pipelines, within the network, by varying the pressure. Increase the pressure, you increase the amount of gas that you store in the lines. The key with this type of storage is that the pipeline itself is kind of acting as a buffer. It compensates for those fluctuations of supply and demand, and you can apply the same principles to hydrogen. In terms of pros, you're potentially utilizing your existing or dedicated infrastructure, very useful for that short-term balancing of supply and demand. You've got a fast response and potentially a low additional storage cost. However, you do have limited storage capacity. You are limited by the number of pipelines you have in use, and really you're looking at short-term storage here. You've got material durability issues for any gas, including hydrogen. But with hydrogen, you've got an additional factor to consider, which is embrittlement. The hydrogen itself is so small, it can actually wiggle through the cracks in a few metals and escape, causing your fatigue in your metal itself. You can overcome this using something like a polymer liner, but again, additional consideration. And the big one for hydrogen is that it has 1/3 of the volumetric density of natural gas, which means you can store 1/3 of the energy inside your pipeline if you were compared to natural gas. In terms of examples of pipelines, hydrogen pipelines are well used industrially, they're well used commercially to transport hydrogen. And they're used for natural gas as well in grid balancing and buffering of that distribution network. But there's some really interesting research coming up on the potential for longer term storage of hydrogen underwater using things like pipelines. And I've linked an article there in case you find that interesting. Final two I'm going to go over, materials-based and solid storage and liquid hydrogen carriers. So for materials-based methods, this is where your hydrogen is stored either on the surface of a material or within a material. And for your liquid hydrogen carriers, this is sort of compounds that can absorb and release the hydrogen through some kind of chemical reaction. So starting with the materials-based methods, lots of options here. I want to highlight to you two main classes. The first are the absorbents. This is where you're storing within a material. So the hydrogen reacts and forms a chemical bond. Typically, we use something called a metal hydride. And the others are adsorbents. This is where your storage of hydrogen is on the surface of the material. So the hydrogen stays as a molecule, stays as a molecular hydrogen, and you use materials such as porous carbons, zeolites, and metal organic frameworks for these. Now, there is a significant difference. They sound very similar, but there is a significant difference between these two kinds of storage materials. And actually, the best way to think about the difference between the two is to think of the analogy of a custard pie. So absorption, with a B, which is what metal hydrides do, is a way of taking molecules in. So like a sponge takes in water, imagine you're eating a custard pie, you're absorbing it. This is the process that metal hydrides use to store hydrogen. They absorb it. Adsorption is the process of a molecule sticking to the surface. So imagine taking that custard pie and rather than eating it, you throw it in someone's face. Carbons, metal organic frameworks, zeolites, this is how they store hydrogen. The hydrogen adsorbs onto the surface. Some important things to know about absorbents, about hydrides. So in these ones, this is where the hydrogen is absorbed into the metal. It forms a strong chemical bond to create a metal hydride. They're very stable compounds, but because that bond is very strong, you can actually store hydrogen at sort of low or in some cases even ambient pressures, which is really interesting and why these are getting a lot of research interest and development. You do need to use heat to release the hydrogen. It depends on the material. It can be up to about 150 to 300 degrees. You heat up the metal hydride and it releases the hydrogen back out again. That process is slower than using an adsorbent, which we'll talk about in a second. But the real advantage of metal hydrides is that that hydrogen does stay locked in that material until it is actively removed, until you want to remove it. So adsorbents, the other process. So this is a surface effect. The hydrogen doesn't form a strong chemical bond. It forms a very weak bond with the surface. And our adsorbent materials, they are made up of a very high surface area of lots of tiny holes. And this is where we store the hydrogen and increase its energy density. The best size for storing hydrogen is very well known. It's 0.7 nanometers. Just to put that into comparison, your very own DNA, the width of that is about 2 nanometers across. So the width of a hydrogen storage pore is half the width of your very own DNA. They're absolutely tiny. They're minuscule. They're very cool. And this is where I did my research, by the way. So this is, I find these particularly interesting. But in these materials, the hydrogen sticks to the surface and it condenses in the pores, and you can actually find that it forms this almost solid-like density within these pores. Now, because it's not a chemical bond as such, it's a very weak bond, it means that this is a very reversible process. You just change the pressure, change the temperature, you can get the hydrogen back out again. It doesn't leave much hydrogen in the material either, which is great, which can be a problem with some of the hydrides, is you get hydrogen kind of left in the material. The caveat to this is that they don't work very well at room temperature, so you need to cool them. So really with adsorbents, you're looking at cryogenic systems where we use liquid nitrogen temperature, which is minus 196 degrees Celsius, 77 Kelvin. Much warmer than liquid hydrogen, but again, still quite cold, so you've got that additional energy consideration there. Just going to summarize those materials into one. Materials-based methods are where hydrogen is stored either on the surface of a material in what's known as adsorption or within the material known as absorption. Pros here, we can get some very high volumetric energy densities, particularly with hydrides. And the hydrides can operate at ambient pressures, which is really, really interesting. Adsorbents can also be used to reduce the pressure required for compressed storage, particularly if you're doing a cryo-compressed system. And these are very stable systems. In terms of cons, these materials are still very much under development. They are a relatively low technology readiness level compared to some of the other methods that we've seen so far. These densities also sound very impressive, sort of hydrides 12 to 15 megajoules per liter, but this is a material storage target, not a system target. System levels. In terms of that's that difference between storing sort of the storage medium itself and the storage medium within a hydrogen storage system. As a rule of thumb, generally divide by 2 to go from the material to the storage system. So they are impressive numbers, but that is for the material. In a storage system, it's going to be lower, but still potentially on par with liquid hydrogen or even slightly better, which is, again, really interesting. These materials can be quite heavy. They do add to the weight of the system. So you've got a consideration there for your gravimetric hydrogen storage. You may increase your volumetric, but you could get a decrease in your gravimetric. There's that kind of that balance, that playoff coming there again. It means they're not always suitable for mobile applications. The release rates of hydrides can also be quite slow, and both sets of materials require some kind of thermal management. Hydrides, you need to heat them to release the hydrogen. Adsorbents, you need to cool them to store the hydrogen. In terms of example applications, so again, these are kind of early technology, but they're looking at them for lots of different kinds of hydrogen storage. Stationary storage is a big one. Cryocompressed storage, particularly for adsorbents, is another big area. They are looking at them for mobile storage, particularly hydrides, and there's some really interesting stuff actually with hydrides in terms of grid storage. There's a project that I've linked you to here called HYDRS, where they're looking at storing hydrogen in depleted uranium. It's worth saying that hydrides actually do have some quite some niche commercial applications already. For example, there's a company called Horizon Fuel Cell. They have an educational arm, and they have these little battery-like devices where you can refill them with hydrogen, and they've got a metal hydride in there. So you can refill with hydrogen, and you can kind of plug it into a hydrogen fuel cell, a bit like you would in a normal battery, which is really interesting as well. So in terms of liquid hydrogen carriers, this is where your hydrogen is chemically bound to a liquid compound for transport and for storage, and you react it to get the hydrogen back out again. I'm not going to go into too much detail here because we do have a future webinar which is going to give you a bit more information on this topic in terms of ammonia. In terms of pros, you can handle them like a conventional liquid fuel, which is a big pro. You can use your existing infrastructure. They've got low pressure and ambient temperature requirements, which is amazing. In terms of cons, they can require high temperatures in order to release the hydrogen. They can require expensive catalysts, and the reactions to both ways, both to store and release the hydrogen, can be quite slow. Examples that they're looking at liquid hydrogen carriers for, international shipping is a big one, any kind of large-scale transport of hydrogen as well, in addition to some longer-term storage. So that's kind of a whistle-stop tour of some of the key and upcoming hydrogen storage technologies. And just kind of to finish up, with any technology, we need to go back to those big three considerations, which is how much hydrogen do you need to store, how much energy do you need to store, how long do you need to store it for, and how quickly do you need to get it back out again. We've kind of covered why we need to store hydrogen, why it's necessary in the first place, and it's all about balancing that volumetric and that gravimetric energy density. What we want to do is increase that volumetric density whilst maintaining a reasonable gravimetric energy density too. I've outlined some key technologies for you. We've had the compressed gases, liquid hydrogen, underground storage, solid state and chemical storage, and we've kind of had a look at some of the pros and cons of these methods, as well as some examples of applications. I think really important to take note of is there's not a one size kind of fits all solution. Each method will suit different scales, different sectors, different timelines. As an example, compressed and liquid hydrogen are mature technologies that are being currently used, but we're a bit limited by the infrastructure and the energy cost. Underground storage, really promising technology, a tool for the storage of large-scale renewables, but needs some continued investment and development, and we're starting to see some of those big projects kind of coming in. For materials-based and chemical carriers, they offer some really high capacities and exciting sort of ambient storage, sort of atmospheric pressure, ambient temperature storage options, but again, they need more development as well. And so looking ahead, so I believe very strongly there is a role for hydrogen alongside other storage technologies. If we're looking at large scale storage, that kind of long duration storage, that critical to solve that critical need for renewable energy balancing, things like salt caverns, liquid hydrogen carriers can be very useful. For our smaller scale systems, sort of our mobile off-grid power backup, these could benefit from solid state storage and maybe some cryo-compressed solutions. But sort of innovation and integration really is the key. Your storage technology has to align with your application, and you have to have that market in mind. And we in the Southwest, we're in a really strong position to drive these kind of regional demonstrations and contribute to that national strategy. And this is what part of GW Shift itself is driving towards. And I will finish on that. Thank you very much. I hope you found this useful.
Thank you, Gemma. That was a great whistle-stop tour through all the different types of hydrogen storage and why they're important in which applications. I do have a few questions in the chat. If you have any questions for Gemma, please pop them in the chat, and in the next sort of 20 minutes that we have left, we will talk those through and see if Gemma can give us some insight and answers.
Try my best, I promise.
So I'm going to go to the first one that I can see. Hi, Gemma, appreciate it if you could expand on hydrogen storage. Sorry, the chat's sprung up, so I've missed it. There we go. Expand on hydrogen storage in pipelines. Specifically regarding hydrogen leakage, would this require upgrading the existing natural gas pipelines, or were you referring to the installation of new pipelines for hydrogen transfer?
Great question. So worth saying, leakage is a problem in with any gas network. It's a problem with the natural gas network too. For hydrogen, you do need typically a polymer liner in that pipeline to prevent that leakage, because you have that additional problem with embrittlement. There's some really interesting work that's being done looking at natural gas and hydrogen blends, and you can it seems you can blend up to about 10% hydrogen into natural gas without having much effect on the system itself and your boilers and everything that come after that. And you can push up to 20%, but you start to see issues with how it interacts with things like your gas boiler. You start to get decreases in lifetime at that point. So in terms of I guess specific storage for hydrogen in pipelines, you can definitely do it if you have a hydrogen pipeline. But I think a big issue for me is that you've got that 1/3. You can only store 1/3 of the energy density for hydrogen in a pipeline compared to natural gas. It is a way of decarbonising natural gas. There's arguments for blending of natural gas and hydrogen and not blending. Some people say at least it reduces some of the carbon impact. Some people say if it's only 20%, might as well go the whole way and do all of hydrogen. So there's I guess advantages and disadvantages to both. there's some really, I've not really looked too much into it, but there's some really interesting upcoming research on kind of storing hydrogen underwater, in which you would use pipelines as part of that. I don't know too much about it, so I unfortunately can't say much about that. But I think in terms of just using the pipelines themselves as the storage medium, you'd be probably looking at something more like that for hydrogen rather than the distribution network itself. So I feel like I went a few tangents there. I hope that answered that question. Yes, you can do it. There's some considerations. Volumetric density is a really big one to consider. If you're going to use them specifically for hydrogen storage, I think you want to look at some alternatives like that underwater storage where you're using the pipeline as part of a specific storage system, rather than just relying on the hydrogen that's in your distribution network.
Thank you. No, that was a really, really good answer. So kind of following on from that, how do we make sure hydrogen storage doesn't leak and it is safe? You mentioned that a little bit just then. What role does inspection play?
Oh, great question. So let's have a think here. So the thing with hydrogen is, I've got a pocket slide here that might be useful. So the thing with hydrogen and leakage is you kind of need to consider its properties and how it compares to natural gas. Frequently, when we're talking about hydrogen, natural gas is a natural comparison point for it because it's already a well-established technology. We've got a lot of certifications and regulations for natural gas. So, and they're not dissimilar, but there are some key differences. The thing with hydrogen is that it has a very high diffusive, it has a very low specific gravity, so it's very light, it's lighter than air, and it rises very quickly. It's very small. That's why it's particularly good at escaping from different things. But it does diffuse very, very well in air. The diffusivity, which is how well it disperses in air, is 4 times higher than natural gas. So if you've ever had a gas leak, it kind of sits in the atmosphere. You can smell the additives that they add to natural gas. Hydrogen diffuses much more quickly. This means in an outdoor environment, it rapidly escapes and it dissipates. So in terms of, I mean, obviously it's not great to have your hydrogen pipeline leaking, but in terms of actual risk for leakages in outdoor environments is actually, because it escapes and diffuses so quickly, the risk is actually mitigated quite quickly. In terms of indoor environments, leaks become much more serious because you can get a vapor accumulation, you get that hydrogen rises to kind of the top, and you get these areas of local flammability. So I feel like I've lost the question as I've been answering it there. So what was it again?
No, that's fine. So how do we make sure it's hydrogen storage doesn't leak, it's safe, and what role does inspection?
That's cool. Inspection will play a massive role. In terms of leakage, there comes a point where you're going to get some leakage of any gas you have in a pipeline. No system is ever perfect. You can certainly minimize that leakage. Particularly for hydrogen, inspection is absolutely critical. You've got to keep an eye on your pipelines. Fittings, or connections where you change between pipelines, those are always the areas where you expect to get a bit more problem for leakage. So yeah, very important. Absolutely. Hope that answered the question.
Thank you, Gemma. And I know that there are already a lot of new technologies around natural gas leakage detection in infrastructure. So I would think it wouldn't be a million miles away to be able to do the same for hydrogen. So
yeah, and actually there's a lot of research in hydrogen sensing and detection. We actually have some colleagues here at Bristol that are looking at this exact thing. It's maybe something that's, I think, is the problem behind detecting those hydrogen leakages, I think, has become more prevalent as in the last few years as hydrogen has become more popular, and so there now is quite a drive to develop this technology to detect these, especially these very small hydrogen storage leaks, these very small hydrogen leaks.
Yeah. Okay, that sounds good. And I guess if it dissipates very easily, then it can be harder to actually capture that.
Yes, blessing and a curse. It does dissipate quickly, but then you have to, yeah, it's harder then to detect.
Brilliant. We have another question. Somebody said, thank you for your wonderful presentation. In your discussion about hydrogen absorption, you mentioned that heating can remove hydrogen. Could you clarify how this applies to gaseous hydrogen during transportation? Specifically, if I'm transporting gaseous hydrogen and want to maintain a certain temperature outside and inside, not sure about that bit. Will this affect the absorption rate?
I'm not sure I fully get the question, so I'll do my best. But please do, if I don't answer it properly, please do ask again. If we don't answer it online, we'll certainly answer it offline. So with material hydrogen storage, I just go back here. So with these absorbents and adsorbents, with the absorbents of metal hydrides, you are chemically reacting the metal and the hydrogen to form a chemical bond, a strong chemical bond. They're relatively stable. In order to release that hydrogen back out again, you do need to heat it up. However, if you are just, so if you're transporting your hydrogen from one place to the other using a metal hydride, for example, then okay, you'll need to keep it at an ambient temperature so it doesn't go over the temperature at which it's going to release the hydrogen. But they're fine and stable for transport. When you want to get the hydrogen back out again, you do then need to heat that up, and that will need to form part of your application, your system, your use case. With adsorbents, the temperature I'd say is probably more critical here in terms of storage for your adsorbents. This is because they store hydrogen basically at cryogenic temperatures, at liquid nitrogen temperatures. If you heat it up or if you change the pressure, you will release the hydrogen. In some ways, that's amazing because you can really easily release the hydrogen quite quickly. On the other hand, you do have to keep that temperature cold. So if you are transporting around a material or hydrogen within an adsorbent system, then yes, you will need to keep it cryogenic. If you increase the temperature, then it will start to release the hydrogen. But that's not dissimilar to liquid hydrogen. If you increase the temperature, you will start to boil off your hydrogen into a gas rather than keeping it as a liquid. So temperature is important for both of these systems. I'd say in terms of actual transportation, it's more important for your adsorbent system. In terms of usage, it will be more important for your hydride system because you need to heat it at point of use to release that hydrogen.
Great. No, that was a really good answer. There is an additional part. How can hydrogen-based failures or embrittlement in materials be mitigated? Will maintaining temperature have any effect? And any suggestions would be greatly appreciated.
Great question. I have to say, hydrogen embrittlement is not something that I am an expert on. I have to defer you probably to our transportation colleagues for that. However, I'll give it my best shot. So hydrogen embrittlement occurs, so not all metals, but some metals, where the hydrogen is able to get into the lattice of the metal framework and kind of wiggle its way through and escape into the atmosphere. As it does so, it kind of pushes aside those atoms and creates this crack, this defect within the metal. Where you've got a defect, you've got the potential for further fatigue and further cracking. In terms of temperature, I imagine temperature will play a role. However, I would not confidently be able to tell you what the problem with the temperature is. We know, for example, that different metals fatigue at different temperatures. Hydrogen will have an impact here as well. What was the second part of that question again? Sorry,
Karen. Will temperature have any effect? Was it so? How can hydrogen-based failures or embrittlement in materials be mitigated? Mitigated, and how can does temperature have an effect in that?
Yes, I would expect it to have an effect. I wouldn't be able to tell you exactly what that effect is. So I will defer to our colleagues in the transportation side of GW Shift for that when we get there. For the mitigation, yes, you can mitigate against it. You need to use material. Not all materials are susceptible to embrittlement. So you need to use a material which reduces that chances. Polymers, plastics, for example, do not have the same problem as some of these metals. So a lot of the mitigation, for example, with the hydrogen pipelines is you're putting some kind of liner within your pipeline that prevents and reduces that embrittlement. So there definitely are mitigations available for hydrogen embrittlement, and it is not a new problem. Hydrogen is used industrially, sort of around the world every day, and it's transported in pipelines. It's transported in metals as well. So this is not necessarily a new problem, but it's probably I would say a growing problem as your network of hydrogen increases.
Sure, and I guess people may be thinking outside of the UK in terms of usage, and so very cold places versus very hot places, and how that could affect any network.
No, definitely.
Thank you. So we've got another question here. I think we've got time for this. Yep. So this one's from Mike Barber. Periodically, there is some excitement about hydrogen-powered aircraft.
Okay.
The technical challenges seem stacked against this type of usage, or is significant progress being made?
Great question. Really tricky one. So in terms of hydrogen in aircraft, really your option is liquid hydrogen, because you need that energy density, and you don't get that with currently any of our other storage technologies. So they're looking primarily at liquid hydrogen. That has quite a big technological jump in terms of you've got a lot of infrastructure there, as I hope I demonstrated, in order to keep that hydrogen cold in the aircraft. There is quite a lot of significant interest in this area. There's been a couple of big programs where they've been looking at hydrogen aircraft specifically. The ATI did one called Fly Zero in the UK. And Airbus have a program as well, but they've just delayed their program, I think partly because it is still a big technological challenge. I guess my view on this is it's really tricky. In terms of our available technologies for aircraft, I think honestly liquid hydrogen is probably one of the only ones that we can actually use feasibly for both short and long haul, because even you may think it's only a long haul problem, but it's a problem for short haul too, because even you have a short haul aircraft, if you actually look at the kind of the flight path that say an EasyJet aircraft takes, it doesn't just go from London to Madrid and back again. It kind of typically hops around quite a lot, and so your refueling, you need quite quick refueling in order for them to meet their targets for that turnaround. I know that's certainly one of the things they're more concerned about for their storage technology. Batteries are quite heavy. The charging time of battery is trickier. You'd have to have you probably could do it with batteries. I know they're certainly looking at it, but it is problematic. Batteries tend to be quite heavy. But liquid hydrogen really does plug that gap. However, the space requirement for the aircraft is quite big. You're losing, if you ever have a look at any of these concept aircraft, you're kind of losing about half of your passenger and your freight requirement, which is a problem when you're operating a commercial airline. The other option, of course, is to use sustainable aviation fuel, of which I think about 10% of all aviation fuel is actually sustainable aviation fuel anyway, due to cost. But you are still emitting carbon dioxide. There's a big argument that we certainly won't go into here about whether they are net zero at all. And you've really got a supply and demand issue for SAFs as well, a big supply and demand issue. They can't get enough SAFs effectively at the moment. They would like to use more, but it's not really possible. So really tricky with hydrogen aircraft. I think long term, if you want to completely go net zero for aircraft, it's really got to be hydrogen. It's got to be liquid hydrogen at the moment. There are some big technical hurdles to overcome to get there. But there is some progress being made. It is moving. But yeah, tricky, but very good question. Thank you.
Oh, yeah, interesting. It's one of those conundrums. But I'm sure that we'll get there in a number of sectors using hydrogen, and some of them already are. So I've got a question from our own Professor Tim May.
Oh,
Fabulous talk, Gemma. Thank you. Can you comment
no.
on so-called white or naturally occurring H2, which is produced and stored in deep geological formations and leaks to the surface?
Yes, I can't comment too much about it, to be honest. I know it exists. I've seen some really interesting articles on Nature and Science about it. But yeah, no, it seems to be a new phenomenon that no one really knows that much about, and they're looking at it. Now, I guess it's probably how you store it would be an interesting question. I guess if you could drill down and somehow tap it and put it into a storage system, that would be really interesting. I don't know what the quantities of this hydrogen generation are like as well, I have to say. I might have to throw back to James for the hydrogen production side for that one. But I think it's really interesting. I mean, naturally occurring hydrogen is great. In terms of engineering problems, things that we need to utilize, there need to be enough of it. It would need to be high purity hydrogen. Typically, a lot of our applications, particularly for fuel cells, use high purity hydrogen. I don't know what the purity is like of these, for example. We'd need some way of kind of trapping it at scale and trapping it and storing it at scale as well. So those are the kind of immediate challenges I can think of in terms of naturally produced hydrogen. But I have to say, it's not an area I know a massive amount about, but it's something that I saw and was like, oh my God, that's really exciting. I hope there's more of this.
I think both Tim and James commented on it in their presentations, and I'm sure we
Tim
will
already knows the
have
answer
others
then. You know the answer.
commenting on it as we go through our series. So I do have some more questions. I'm not sure I'm going to get through all of them, but hi, based on your expertise, do you believe that abandoned mine sites represent a technically, economically, and environmentally viable option for large-scale hydrogen storage?
Good question. I mean, potentially, it's certainly, I think they are looking at them, but they are, I think it's not one of the leading underground technologies, probably because it's not really been done much before, and there's a lot of additional expertise that they'd need there in order to do that, and certification and regulation. So, I mean, I guess you could use any, I guess you could technically use any underground space. It really depends, I think, on the geology of the area as to whether it's suitable for encapsulating and storing your hydrogen. I imagine that would depend on the mine that you're using. I have to say, I won't be able to give you a definitive answer for that. Possibly will be geologically dependent on whether you can actually use it to store the hydrogen gas and prevent it from leaking. Same with any underground gas storage. I think they were looking at them for methane as well, but I don't know how far along they got with that. I have to say, but yeah, maybe.
Thanks. Thank you, Gemma. Well, I think we can just squeeze in one more question.
Yeah.
Appreciate your wonderful presentation. This is from Arcana Desia. I probably said that name really badly, sorry. Great presentation, very clear. How can nanomaterials improve hydrogen storage efficiency? Interesting question.
Nanomaterials. So it depends what you class as a nanomaterial. I mean, if we're talking about adsorbents, some of these are already nanomaterials in that the particle size can be nano. Certainly, they have nanopores. If we mean things like carbon nanotubes, there was a bit of a controversy about hydrogen storage controversy about storing hydrogen in something like a nanotube because they weren't sure if the hydrogen would actually enter the space of the nanotube, and it seems that it's not entering that space from what I've seen so far. And so the nanotubes themselves have kind of waned in popularity as a storage medium. I think the thing with nanomaterials is that we store hydrogen in these nanopores. These are 7 angstroms, 0.7 nanometers across. The hydrogen does need to be able to get in there. I think your limit is about 5 angstroms or 4 based on the size of the hydrogen. If the pores are too small, you won't get the hydrogen in. If the pores are too large, you kind of get this waste space in the pores where you can't densify the hydrogen. You can't get to that solid-like density. Yeah, it depends on the material. It depends on the properties. You need small pores to store hydrogen. 0.7 nanometers is the ideal. it does need to be able to get in there. So something like carbon nanotubes as a nanomaterial didn't really work very well because the hydrogen couldn't necessarily get into that pore. It instead was kind of being stored sort of in the gaps between the nanotubes instead, which is, you know, still storage. It's still useful, but it wasn't at the sort of, it meant you were restricted in that kind of really high energy densities that you could possibly get with a nanotube.
Thank you very much, Gemma. I think we're going to wrap up there. We're at 1 o'clock, so we're on time. But thank you very much. If you want to just stop sharing your slides, that would be great. And thank you everyone who has joined us today. Very, very interesting talk. We do have more questions, so we will commit to getting a time where we can record those, and they will be put up. And perhaps we'll be able to point people to some other areas where there was things slightly outside your field, because of course nobody knows everything when it comes to hydrogen, although I'm learning a lot as we're going through. So thank you very much everyone for joining us. Make sure you're here on the 9th of May. We'll be sending the link out soon for that, and please take care. Thanks everyone.
Thanks everyone.
Bye.
Take care.
Thank you.
Bye.
Thank you.